Okay, so welcome. We are going to start our week 7 from this particular module. So we have already finished half of the course, so remaining half is left, and I hope you are enjoying the course so far. If you have any questions, any concern, feel free to contact us through the discussion board. So we'll continue our discussion from where we left in the last week's last video, where we were looking at composting, different factors, environmental factors which affect composting. If you remember, we were talking about the temperature, we are talking about the pH. So we'll continue the discussion further and look at some other factors which is out there. So in terms of the other environmental factors, one of the important stuff, say composting is an oxidation process. So when we say oxidation process, we have to calculate the amount of oxygen required. So that's what I'm trying to, this was what this slide is trying to say, that you have to find out the amount of oxygen required, because that's what when you are, it's a oxidation, so you are supplying oxygen. So oxygen, when we don't supply oxygen, we supply air, and oxygen is part of air, around 23%. So that's we will be supplying air to this system. So we have to find out how much air is required. So for that, first we will find out how much oxygen is required, and then we know what if this much amount of oxygen is required, what is the proportionally how much air will be required based on the percentage of oxygen present in air. So we have to calculate the oxygen, and that can be done using following a stoichiometric equation. So here you have the formula of the waste, and now here what is this? If you remember from that slide that we had earlier, this will be the biological volatile solid. So it's the BVS. If you remember that pie chart we had, where you had like you had the BVS portion, you had some water. So we had water here, we had we had the inorganic fraction over here, then we had this RVS, residual volatile solids, and then we had VVS. So not a great, it's a BVS, biological volatile solid. So that's this so we have to find out, this formula actually relates to this part of the pie, because that is what is going to react. Other things will go into the system and will become part of the compost, or will like it is not going to react in the system. So what is going to react is the BVS portion. So since we are writing the equation here, like what is going to react and how much oxygen we are supplying, and these are the products that are being formed. So we have to take the fraction which is going to react, which is the BVS fraction. So it's a biological volatile solid fraction. So for the waste material that is coming to your plant, say if you are designing a compost plant for whatever city you are working for, you are designing a compost plant, you should know what is the BVS fraction, you should know the composition of the BVS fraction, and then so that you can come up with this equation. And we'll do a math to see how these equations, how these formulas can be derived. You can if you do the CHONS analyzer, if you do that carbon, hydrogen, oxygen, nitrogen, how much is there, you can always come up with a formula for that. So we'll talk about that. So we are, and there are different ways you can add air. So if we're using this equation, we can find out, we know this formula. So we can, once we know this formula, because based on the BVS fraction, we can do that analysis of the waste sample and can get this formula. Once we get this formula, we can, using a stoichiometry, here what we are doing, we are assuming that entire fraction of BVS is going to react. So the entire fraction of BVS is, it's an ideal scenario, like it's a 100% reaction conversion, which normally doesn't happen, but for our calculation purpose we can use it, because we can use always a factor of safety here anyway, because once we get this oxygen, we'll apply a factor of safety. So this is a additional factor of safety you can think about. So once we know this formula, we can find out how much oxygen is required. So once we know how much oxygen is required, there are different ways you can have this oxygen added to the system. You can have a forced aeration system. You can have a forced aeration, where you have the static piles and then you add air to it, you are forcing air through, or you have in-vessel systems, you can have the in-vessel systems. And then here the total air requirement and airflow rate, these becomes the essential design parameters. So if you have to design that system, your air requirement and the airflow rate, at what rate you need to pump the air, that becomes one of the essential design parameters, because you need to that's your essential design parameters for doing the design system. And and then you can do windrow composting. Windrow composting, how we add air, we keep on turning the waste. We turn the waste from time to time. We bring our waste turner and we turn the waste. While we are turning the waste, air is getting into the waste pile. So that's how mixing and turning of windrow, that's which is done in terms of composting. And if you don't do the mixing properly, and if the air does not flow really well, if anaerobic pockets gets built up, what happens is you will have the problem of a smell. You will have the odor problem. So it's a good mixing and turning to intern air, and good air circulation system is one of the critical factor in terms of the compost design. Because if you if you have the odor issues, if you have the smell issues, if you are your neighboring industry, or if you have a residence neighborhood, they will start complaining, and then you will have issues with that as well. Actually, in London, Ontario, which is there is a London in Ontario in Canada as well. So there's in London, Ontario, as well as they had a Orga World is one company, which is a very big company. I think it's essentially the parent company comes from Netherlands. I'm not 100% sure, but I'm 99% sure. So yeah, I think it comes from Netherlands. And then this Orga World was having a plant in London, Ontario. The nearby residences complained against the odor issues coming from the plant, and they had to shut down the plant to set up a odor removal system. So there are odor removal system in a landfill, in a compost plant as well. And with the time permission, we'll talk about that. I had a master's student did a thesis on odor removal technologies, techno-economic as well as life cycle analysis of the odor removal technologies from a compost plant. So if time permits, we can talk about that particular research. If we get otherwise, if you're interested, send me an email. I can send you the paper that we published on that. So, but odor does become a problem. So, good mixing of air, good circulation of air is very, very important in terms of a compost plant. So, that's other factors. Then other thing, you don't have to try to memorize things from this particular table. I'm not going to ask any question, any like a memorization kind of questions from this particular table. But the bottom line that you need to get out of this is that we have to destroy the pathogens. Destruction of pathogen is an important element in composting. So we have to destroy the pathogens, and that's one of the important factors that we have to do. We have to destroy these pathogens, and how we do that. So there are different types of organisms present. You don't have to remember. It's not a you can have some idea. You hear about Salmonella from time to time. This is two types of Salmonella, E. coli, and then there are other bacteria out there. Corynebacterium, Nectarbacterium. So there are different types of bacteria which is out there, which has like if you increase the temperature, especially if you look at on this side, if you look at from top to bottom on this side, you see that if you have a temperature of around 60 to 65 degrees centigrade, and if you keep it for around an hour, most of these bacteria will die. So that's because once you make the compost has to meet the compost standard. There should not be any pathogens in the compost. Otherwise, people will get sick. People handling the compost will get sick, and then it can come into our fruits and vegetables. Because when you apply this compost in agricultural field, these pathogens can come to the fruits and vegetables as well, and which you don't want it to happen. So in that case, what you need to do is you need to, as part of the composting process, once the waste has degraded quite a bit, almost towards the end of the composting process, there is a phase when we increase the temperature to around 65 degrees centigrade. We don't want too high of a temperature, because if it goes beyond 70 degree, what happens that the bacteria, the good bacteria the earthworms they starts dying. So you don't want that to happen. The aerobic set of bacteria which we need for composting process, we don't want that to die. So that's why we don't want it too high. It's around, we try to keep it around 65 degrees centigrade, because above 70, many of these good bacteria starts to die, which actually bacteria does the work for us, isn't it? A composting is an aerobic aerobic exercise where these microorganisms, these bacteria are working on our behalf and doing the degradation of organic matter. So we don't want those bacteria to die, so we just keep it at around 65 for 1 hour. As you can see from this part here, that if you keep it at 65 degrees centigrade for 1 hour, all these pathogens, they die away. As you can see, no growth beyond C46 after destroyed, and after up to 60 degree, death within 1 hour at 55, 5 to 15 to 20 minutes at 60. So if you keep it above 60 to 65, most of these pathogens will die, and you will have a cleaner compost from pathogens perspective. Then air requirement. So we'll try to do a math now in terms of how to calculate air, because that's one of the most important parameters that you need to do in terms of when you try to go for a compost design. One of the important parameters that we need to do is to have a aeration system. So for development of the aeration system, we need to know how much air we need to add. So here, one is given. So if you have look at, if you have an amount of air required. So in this problem, it says amount of air required to compost 1 ton of solid waste using an in-vessel composting system with a forced aeration. So we are trying to add air to it. So we have been given composition of the waste. So the formula of the waste is already given. How this was derived? The composition, as you can see, C60, H94, oxygen 38, and nitrogen. If for certain types of waste, certain types of agricultural waste, based on the people's research done earlier, there are some compost books out there. From there you can get the formula directly. But if for many cases, what you need to do is you need to take the sample, get it analyzed, then you know how much carbon, hydrogen, oxygen, nitrogen is there. You do an ultimate analysis, CHONS analyzer, and then you can come up with this formula. The moisture content is given of the organic fraction 25%. Vs is 0.93 of the total solids. 93% of total solids. Now the biological volatile solid is 60% of the volatile solid. Expected efficiency is 95%. So here it tells you that not 100%, but 95% is actually reacting. Composting time of 5 days is given. Oxygen demand is given, like how the oxygen that is required is distributed over 5 days. So first day 20%, second day is the highest, which is 35%. Then ammonia, we are assuming that ammonia produced during the aerobic decomposition is lost to the atmosphere. We are assuming that also it's a fact. We are not, like, air contains 23% oxygen by weight, and the density of air is 1.2928 kg per meter cube. And then we'll use a factor of safety of 2 to assure that oxygen content does not drop below 50% of its original value. So we have a factor of safety of 2 there as well. So this data is provided to us. So using this data, if you have to do the math, and as I said earlier, solid waste maths are not that difficult. Again, now here, if you look at the composition, just to remind you, this is what I was trying to draw a few slides back. You have the water, you have inorganic, you have residual volatile solids. Oops, sorry. You have residual volatile solids. So these is not going to react in the compost system. What is going to react is this part. So this biological, that the equation that we have for the formula that we have is actually for BVS fraction. So that formula is already provided to us. So we have to calculate the air requirement. So first thing to do is to find out the total dry mass of air. If you remember from the previous slide, it says 25% moisture. 25% moisture means 75% dry. So if you have 1 ton, 1000 kg. So what is the mass of total solids? Why we need total solids? Because we have been told that volatile solid is given in the form of total solid, is 93% of total solid. So we have 93% of total solids here. So that's, we are using 93%. That's 93%, and then we got volatile solids. Now once we know the volatile solid, we have been told that biological volatile solids is 60%. So we take this number, then 60%. So we got that number, like a mass of biological volatile solid. Now out of the mass of volatile for BVS, 95% is what is going to react. So conversion is 95%. So what this number, 95%, we get 397.6 kilograms. So that's the mass of BVS. Now this is in mass. If you remember from the equation, if you write any equation, you have 1 mole of this will react this many moles of this to produce this many mole of these products. So we have to convert things in moles. So how we'll convert the things in mole? We'll take the BVS. We had already had the equation for BVS fraction, so we can find out the molecular weight of that BVS fraction. So the mass of molecular weight based on C60, H94, oxygen 38. So for this particular, if you look at the mass, so 60 times 12 is for carbon, hydrogen is only 94 times 1, oxygen is 38 times 16, and nitrogen is 1. So once you add this up, you get 1436 gram per mole. So this much gram per mole is there in terms of the molar mass of the BVS compound. So once we have this molar mass, we can calculate what is the total amount of so once you have the molar mass, so this is this much moles, we can find out in terms of amount of moles of oxygen required. So amount of moles of oxygen required is for one mole of this, we can just plug the numbers here, 4a plus b minus 2c minus 3d upon 4, that's the how much, like 1 mole of that particular material will require these many moles of oxygen. So A, B, C, D we can get from this here. A is 60. So A, B, C, D is what from coming, A, B, C, D is essentially coming from your CA, you have CA, HB, OC, ND, and if you remember, that's how we have defined it in the previous equation. So from the previous slide, if you see it, A is 60, B is 94, hydrogen is 94, oxygen is 38, and nitrogen is 1. D, that would be nitrogen, D is 1. So we can plug these numbers over here. So 60, 94, 38, 1, and then you get 63.5 moles. So for 1 mole of this particular material, we need 63.5 moles of oxygen. So we know 397.6 kilogram was the mass. This is the molecular weight. So this divided by this gives the mole of waste. So that's the mole of waste, and then you will multiply it by for 1 mole we need this much. So for these many moles you need how much? So you get that ratio of that, and then you get x, which is actually this will go over this side and then become multiplication. So x will be, you get 564.8 kg of oxygen. So you need this many kgs of oxygen for 1 mole of not for this many kgs of waste based on 1 ton of waste coming in. So this is the amount of oxygen is required. So it is expressed in kilogram, and we were talking about flow rate and all that. So we have to put it in meter cube in the volume. So we'll do that conversion. So to convert that way, we will have. So you again before that we'll convert this to a factor of safety of 2. So there is a safety factor 2. So volume of air is 564.8 kg of oxygen. Then we have 0.23 kg of oxygen per kg of air. Then air has a density of 1.2928. So that way we can find out how much amount of air is required, including the amount of air required. Here we have included the factor of safety as well. So factor of safety of 2 has been taken care of in this over here. So that's the amount of air that is required. And if you remember from the problem statement, if you go back to the problem statement in a minute, if you remember from the problem statement, it says oxygen demand is 20%, 35%, 25%, 15%, and 5% for 5 successive days. So these are on 5 successive days we have, this is the oxygen demand. So the maximum is 35% on day 2. So why this information is important? Because once you come back and have this number, once you have come back and have this number where you have this much meter cube of air is required per ton of solid waste. Now this much meter cube of air is required over a 5-day period, because we have been told that composting, this particular process is a 5-day process. So but on day 2 we require 35% of oxygen. So most of the oxygen is actually required on day 2. So when we buy the blower, when we buy this blower system which will blow the air through, the blower has to say that if we have a total requirement and we know it's over day 5, so we just cannot just take the total requirement, divide it by 5 to get individual days requirement. That's not the case, because in day 2 it requires much higher, it's 35%. So it's not, we cannot take the average here. So the pump blower system has to meet the requirement of day 2. If it meets the requirement of day 2, other days are met anyway. So that's the constraint, is the design constraint is having that day 2 scenario where you can supply 35% of oxygen. Based on that, so volume of air is 3799. So on day 2 you will require 35% of that. So you have 1330 meter cube per day. So that much what is needed. And so you can so that's the volume of air that is need to be provided. If you then other problems that you can look at the how much is the mass of water present. Do we need to add some water, because sometimes the compost also require some water requirement, so those things can be looked at as well. So that's the how much mole of oxygen like water present there, and then mass of water that is needed in terms of having a how much based on the number of moles that is will be there. So based on that you can find out how much like a oxygen requirement, water requirement will be there, or even you can find out how much water will be produced. So basically this is some illustration of you can find other informations associated with that too. So that's present on that slide. And then you have you can also find out what's the water required, like what is the mass of water which is required, because during the aeration process you are also losing some moisture. There is a loss of moisture over the period of those 5 days. So initially if you had 25%, and over 5 days if you have a 20% loss of moisture, so you are losing around from 250 grams that you had initially in front of 25%, you are losing around 50 grams, so you are down to 200 grams. So the composting process requires 226.8 kilogram. So somewhere in the 5-day process we dropped below the water need, so we need to add water. So the water deficit usually is there, which is you can calculate that as well. And so to be conservative and applies factor of safety, so you have a water deficit in terms of the compost plant. So that can be like looked into and worked as well. So that's in terms of the water requirement. And then so you can add water. For day 1 the mass of water was actually more than what is required, so you can add over the next 4 days. So you should this should provide adequate water for process to complete itself with no moisture problem. So you have to look at the air requirement. The other thing is that how much moisture is required, whether we have enough moisture, and all those things should be looked into. Now there are different types, as I said earlier, there are different types of composting process. There are some mechanical system, there are some pile, windrow and turn-in system. There should be some static pile. Static, as the name suggests, it's a static, it doesn't move. So things are not moving over there. Some mixing could be done, but not too much there as well. So based on what system you go for, there are different time duration. The one that we just the math that we just talked about was kind of a rigorous mechanical system, because they were talking about just 5 days. So but here the typical your system is around 7 days. When you go for pile and windrow with turning is around like 9 to 21 days, and then static piles or with some mixing goes up to 30 to 40 days. So again it all depends on how much space you have, how much money you can spend. So if you have a bigger space and you can don't want to spend that much money, go for static piles with some mixing. It will go over 30 to 40 days. But that's okay if the land is not an issue. If you have sufficient land available, the cost will be less, and you can operate that the compost that way. In terms of windrow, where you are turning piles and windrow, where you are doing the turning exercise, 9 to 21 days. So it's like around slightly over a week to 3 weeks is what it's required. If you go for a highly rigorous of like a mechanical system, you can even bring it down to a week. So you can get the composting done in the week. So There are different systems, more like as we go up, the cost goes up as well. As you go for this system, your cost also goes up, so you more cost as you make it late. But sometimes the cost of land is so much, because if you have to do it for 9 and 21 days, that means you need a storage space for garbage. You need to have when you do this pile, that's also takes it has the area occupied for 21 days. So if the land is cheaper, then like this too is can work. But if the land gets very expensive, and then it may work out that you may have to go for a mechanical system, because that's how it can get done quickly. So, but when we will know when the process is finished, so that's another part, like how to find out whether the process is finished or not. So, when you are turning the compost, the temperature does not rapidly rise. So, what does that mean? So, when you are doing that compost turning and you don't see, after that you don't see because compost plant we do have temperature probes and all that there to measure the temperature. So, if you don't see it sudden like a rapidly rise of temperature, that means most of the organic degradation has taken place, because organic degradation is an exothermic reaction. It releases heat. So, once when the reaction releases heat, the temperature has a tendency to go up. So, but if you don't see a temperature increase, you don't see substantial temperature increase, rapidly temperature increase, that means the most of the organic fuel is gone. Things have been degraded. The material left over is like a humus-like dark brown. It smells earthy, like it smells of a soil. The remaining compost is half the original volume. So, it's around 50% of the initial mass that you put in there. So, that needs to be kind of sold off or used for different applications. And then the compost is usually then cured for additional 2 to 8 weeks. Once you have done with this initial exercise, you let it do the curing. What the curing does is it produces a large, more diverse microbial population. So, you basically what you are doing here is you are putting it in a favorable condition. You are putting this particular compost pile now in a favorable conditions for it to get matured, to get some moisture, to have the microbial activity going on. Some even like trees planted and all those kind of things could be done on that too. So, it does help in like in compost having a larger, more diverse microbial population, and it does provide a stable source of nitrogen for application to farm land. So, with the carbon nitrogen ratio of less than 25:1, reduces the temperature so that seed can survive. So, the germination test we can do to find out whether the seeds are going to survive, whether it will if it doesn't survive, then there is no point of this compost, isn't it? So, seed has to survive. So, that's what when we have to reduce the temperature for that as well. So, in terms of composting technique, there are two principal methods of aerobic composting, with agitated and static. Agitated is material is agitated periodically to introduce air, and static is the material remains static and the air is blown through the compost. So, the first part, the material is agitated periodically to when we are adding the air, and the second one, material remains static. We are not moving the material, but air is blown through the compost, and we are producing that's how the air is added to it. So, composting technique, windrow composting, it's like typical windrow. Organic material is formed into windrow. You have a 3 meter height, 5 meter width, and the length will be based on your location that is available to us. Then you have a front-end loader or mixing apparatus where it will go, and then it will keep on mixing and turning. Complete composting can be done in 1 to 3 weeks, and then you do another curing where you don't need to do the mixing for additional 3 to 4 weeks. So, that's how windrow composting is done, which is one of the very popular way of doing compost in many parts of the world. And then the other one could be aerated static pile, where you have a blower operation. So, this is you have in case of here, you have some sort of windrow kind of structure. You have some pipes, and you can either inject air or you can apply vacuum. So, when you apply vacuum, the air will have tendency to try to go in there. This material these days are like you have like a daily cover kind of material. So, that is also like this kind of material is used, and then it has some perforation so the air can potentially pass through. So what you are doing here is you are actually applying vacuum. You are applying vacuum and let the air go in there. So that's the one way of doing it. You can also apply positive pressure. So it's a blower operation is typically controlled by a trimmer. So based on temperature, you don't want temperature to go too high because there will be some fire issues as well. So based on temperature, you increase the blower, you start the blower. Once the temperature starts getting too much, you stop, and then the cycle continues. So you can do positive or negative, both pressure, like either vacuum you apply. Material is composted in 3 to 5 weeks, slightly less. Then compost is cured for another 4 weeks. So that's is used for composting like a static pile. So that's in terms of the composting technique. So there are two different types of techniques we talked about, and so let's based I think it's we have to wrap up this video now, because and then we'll continue with our second video, and where we try to do some more math calculation for this composting exercise. Then we'll move to anaerobic digester. So again, right now we are focusing on biological treatment of waste. We started this discussion in the previous video. We are continuing into this video, and then will most likely it will get completed in the subsequent video. So again, if you have any questions, feel free to contact and then we will be always be ready to help you. Thank you.